Good morning, all. Today we will be studying about discrete time Fourier transform or DTFT. Now, this actually is your next topic in your syllabus, but DFT, that is discrete Fourier transform, and DTFT, that is discrete time Fourier transform. So, before going into the details, let us have a look at each of it. That is, what is DTFT, followed by what is DFT. So, in this today's session, we learn about DTFT. Okay, its full form is discrete time Fourier transform. Now, as we already know that a discrete time signal is a sequence of numbers. It can be either real or complex. Now, it can be converted into a complex frequency domain using Z transform. So, Z transform is nothing but a mathematical operation or an effective tool that links time and frequency domain of discrete time signal given by x of n. Now, discrete time systems have certain properties like low pass filtering and high pass filtering. So, and it is necessary to transform this complex Z plane to real frequency axis for specifying each of these properties like low pass filtering and high pass filtering. Now, for this transformation, the region of complex Z plane that we use is a unit circle given by Z equal to e raised to j omega. And the resulting transform is called DTFT or discrete time Fourier transform. So that is the definition of DTFT. Now it can also be considered as a member of Fourier transform family that operates on aperiodic discrete signal. Remember, it operates on aperiodic discrete signal, or it can also be defined as it is a Fourier transform that relates an aperiodic discrete signal with the periodic continuous frequency spectrum. Study those underlined parts. That is, DTFT is a Fourier transform that relates an aperiodic discrete signal with a periodic continuous frequency spectrum. Now, for a discrete time sequence xn, we can define the Z transform x of Z on a unit circle as shown. That is, x of e raised to j omega is equal to x of Z at Z equal to e raised to j omega, that is again equal to summation over n equal to minus infinity to plus infinity x of n e raised to minus j omega n. So that is how we define the Z transform of a discrete sequence. So if you have a discrete time sequence x of n, then its Z transform is represented as x of Z on a unit circle, and its expression is given in that box. Okay, here that function x of e raised to j omega or simply x of omega is called DTFT or discrete time Fourier transform of the discrete time signal x of n. Now, if you want to get the inverse DTFT, it is defined as follows. That is, x of n will be equal to half pi integration from minus pi to plus pi x of omega e raised to j omega n d omega. So, just study the expressions, no need to study the derivations. Okay. Now, next we go to the properties of DTFT. The first property is periodicity. Just as the name indicates, periodicity means something that repeats at regular intervals of time. So, DTFT has this property, that is, it completes a pattern within a measurable time frame called period and repeats that pattern over identical subsequent periods. So, DTFT is always periodic in omega with period 2 pi and is given by x of omega plus 2 pi will be equal to x of omega. Next property is convolution. This I think you have studied in your last semester in integral transforms. So convolution is a mathematical way of combining two signals to form a third signal. That is, if we multiply two signals in time, then the Fourier representation for the product is the convolution of the Fourier representation of individual signals. Okay, now this type of convolution property becomes helpful when a discrete Fourier transform is applied to signals of finite length, and also when you are designing finite impulse response filters or FIR filters. About FIR filters we will learn in detail in the subsequent modules. Okay. So see, let h of n be the impulse response of a discrete time signal, then frequency response of the signal is given by h of n. When DTFT is applied, it becomes h of omega. Now suppose that you have a discrete sequence xn, x of n, then on applying DTFT we get capital X of omega, that is the DTFT of x omega. As I already told, it is a DTFT of the discrete sequence x of n. Similarly, if you have another discrete sequence, so say y of n, on applying DTFT you get y of omega. Now convolution theorem states that if y of n is equal to x of n into h of n, then y of omega will be equal to x of omega into h of omega. H of omega, h of n is nothing but impulse response even to the discrete time signal. Next one is time shifting. Time shifting means shifting of signals in time domain. It is given by x of n is equal to giving y of n plus k. Now this k can be either positive or negative. If k is positive, then we call it by the name positive shifting or right shifting. That is, signal is shifted towards right in the time domain. Now if k is negative, we call it as negative shifting or left shifting. That is, the signal will get shifted towards left in the time domain. So that time shifting property is given here, that is x of n minus n0, that is there is a shift n0. On applying DTFT, it is will be given as e raised to minus j omega n0, the shift into x of omega. X of omega is the DTFT of x of n. Now next one is frequency shifting. Frequency shifting means shifting of signals in frequency domain, and it shows that e raised to j omega 0 n of xn on applying DTFT giving x of omega minus omega 0. So just go through this definition and this expression, and in the above case, what is meant by shift, what are the two types of shift, and then on applying what you get, that is this particular expression is enough. Okay, similarly to that of frequency shift also. The next one is, the last one is time reversal. It can be negative. In fact, one can make it negative just by multiplying it with minus 1, and when you multiply it with minus 1, what happens to the original signal? It will flip along its y-axis. This means that it results in a reflection of the signal, or the signal will get reflected along vertical axis of reference. Now, so this operation is called by the name time reversal or time reflection of signal, and it is that the signal x of n giving x of minus 1, minus n. So here just study what is DTFT, what are its definition or how can you interpret it mathematically, then what are its applications, then its 5 important properties along with the definitions for each of the property and the corresponding expressions. So that's a brief introduction about DTFT. Now in the following sessions we will learn about DFT, and then we will learn how DFT can be obtained from DTFT and like that. Okay, so that's all for now. Today, just learn about DTFT, which is discrete time Fourier transform.